Additive manufacturing, also known as 3D printing, has shattered traditional manufacturing limitations. It's now possible to make structures, materials, and devices that could never have existed before, with wild new shapes, behaviors, and properties. But for engineers, this design freedom can be overwhelming.
Additive manufacturing gives really unprecedented amount of control over the geometry of what we're building and even what material we're using in different locations to do it. And with all that flexibility comes a lot of decision making.
Engineering is all about solving problems, and design optimization is all about finding the best possible solution to a problem. Engineers might reach an optimal design through trial and error, but it could take years and thousands of hours of labor, even for relatively simple problems.
We can literally design over millions of parameters in our optimization, and you can't do trial and error on a million parameters, even if you have the fastest computers. We have to have some more sophisticated means, which our optimization allows us to do.
At Lawrence Livermore National Laboratory, optimization engineers are leading a design revolution by developing computational optimization tools to solve these large, complex design problems at the lightning pace of national security.
Additive manufacturing really opens up a lot of possibilities of what is possible, and design optimization helps us unlock that potential. In some cases, it's letting people solve problems faster than they could before. But another way of looking at it then is that they can tackle more complex problems than they ever could.
Design optimization starts with a goal, constraints on a design, such as cost or maximum height, and variables that can change, known as parameters. Those parameters are then adjusted until a better design is no longer possible for the given problem.
Optimization at its heart is really a mathematical process. You have some inputs, you have some output you care about, and you want to make that output as big or as small as possible.
For example, consider a dam. This flat design might work well, but it would require using an excessive amount of concrete. In this scenario, the design goal would be reducing the amount of concrete used while ensuring the dam is strong enough to hold back water at its highest levels. And the parameters would be the shape of the dam. An optimized solution might look something like this, with a curved arch and some buttresses that place more material at the points where the water pressure is highest. Optimization problems are also specific to the design situation, so optimizing the dam for a different height and/or length would likely result in a completely different design. Now imagine being asked to design the world's most complicated dam without knowing anything about dams, being able to look at other dams for inspiration, or even knowing what a dam is in the first place. This is what makes it so difficult to optimize 3D printed designs.
So it's like baking bread. You can change some of the ingredients and bake a bread and then change it and see how it goes, and then you can tune those ingredients until you get something that is good. When you can control the alignment of physical crystals in the entirety of your design space, the design space of your problem just explodes. Instead of just changing the ingredients of your loaf of bread, you can change the molecular arrangement anywhere in the loaf of bread. You suddenly go from having potentially a few parameters that could affect your design space to having millions of configuration. It's not a matter of time, it's a matter of like, well, will I ever get there?
Using a computer can help researchers tackle these large, complex problems that would be impractical or impossible to solve by hand.
The computer is not limited just by human intuition. It's really following where the physics is pointing it. It's basically using the tools of calculus to figure out which direction should we go.
Engineers at LLNL are advancing computational design optimization by developing and applying two codes called Smith and the Livermore Design Optimization Code, or LIDO. LIDO and Smith automate the most time-consuming steps in optimization and make it relatively easy to try new kinds of materials and structures and solve different types of optimization problems with the same models.
LIDO helps you set up that problem quickly and to find what's the optimal value. How do you move your design in the direction that you have available to you that you get the best performance? Smith runs differentiable physics simulations is what we call it, when it's able to give you not just the response of how your part or your design is doing, but also if you remember from calculus class, the derivative, what's the best way to change it from where you're standing right now to make it even better.
Computing derivatives, also known as gradients, allow us to optimize over high-dimensional spaces. To see how gradients are used in optimization, imagine descending a mountain at night. Since you cannot see, you repeatedly detect the slope of the ground around you and take a step in the most downhill direction until the slope about you is uphill in all directions. This most downhill direction is the gradient. It is easily obtained in this two-dimensional problem by sampling the slope around you. However, sampling is not practical in the high-dimensional problems that engineers encounter with additive manufacturing. Instead, they use highly efficient methods to compute the gradients for these problems.
By having these derivatives, it's really the only way that we can do these optimizations that involve millions of design parameters.
By hand, calculating gradients is a painstaking process that involves difficult calculus. Smith does it automatically.
The beauty of it is you can go through everything very quickly.
A third, probably half of my PhD was computing these gradients by hand. By hand, I mean I was literally writing down continuum mechanics formulation. These days, we don't have to do that.
The engineer, the designer, they're never out of the loop. They set up the problem, they set up the simulation. What I like to say is we're taking the drudgery out of it.
Lido and Smith help the lab's optimization engineers and additive manufacturing experts work together to push the discipline forward.
Our interest is coming up with design optimization algorithms. Their interest is to come up with new manufacturing processes.
For them, showing that they could print a complex 3D gyroid is the end of the project. For us, one final goal is not to find an optimal solution or be happy with our math, is to be able to provide something that is functional.
And so what we do is we combine, and then we say, well, we're going to design a certain widget. And now they can design the manufacturing process that'll create that widget.
In one recent project, the team helped design and optimize 3D printed active materials being developed by experts at the lab. This new class of devices can react and respond to stimuli like light, heat, or electricity. With Smith and Lido's help, the team produced an optimized design in a matter of weeks.
We're learning how the material works at the same time that we're developing the chemistry of these materials. If you use something like Smith, you don't need to spend much time into getting that material model implemented and tested, because it's only literally like a couple hundred lines of code max.
These tools accelerate innovation and give Livermore the ability to quickly pivot into new design spaces to address national security challenges.
If the lab is giving some new system and has to design, we have to do it fast. So the codes we're writing are agile in the sense that they can be modified quickly to design new systems.
As long as you understand the material's behavior, then you can get an optimal solution without having to manufacture those designs over and over again.
Over the past decade, Livermore has started to become a home for optimization research, and the work of the tight-knit team has established a potentially transformational capability for LLNL.
It really builds on everything Livermore has worked on for a long time, which is being a world leader in developing simulations capabilities. And so this is sort of the next level tool that you can bring onto that. And I think that we're really building up a competency here that's special at Livermore in design optimization. I'm just glad to be here while it's happening now.